uh, the recording. Anyway, let's briefly go through the signature operator. We have we have questions. We have a few questions which are basically linear algebra, and but these involve Clifford algebras. Let's talk about those later. The main thing that we need is actually part B. Okay, yeah. I think yes. We basically let's assume that we have the formula from part B of question 14. And part C, which is part C is something which would which we also saw at some point. Well, at least partly. Uh, okay. Uh, okay. Uh, 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 let's uh, uh, let's see. So well, question 14 is basically what we mentioned, what we already mentioned, plus some more information. So let's have a look at question 14. Let's ignore everything which contains mention of Clifford algebras. Let's just look at part B, part C, and see if if they make any sense. Okay. Now let's do question 15C. Uh, and let's do the following thing. So suppose we have a real oriented rank 2 vector quantity. Well, the result is the same as the complex line bundle as a real vector bundle. The bundle E has a natural complex structure. Okay, so now I take E tensor C, and the result is A plus A star. Now I want to define alpha. Which is a map of vector bundles. And alpha squares to 1. And the definition is given in question 14. Part B. Okay, now what do I do with this definition? Well, I want to find the plus and minus eigenspaces. Well, let's see. Normally it's difficult, but we already have this. We already have one decomposition, and we're looking for another decomposition. And could it be that the decompositions are the same? Well, let's see if well, it's a reasonable conjecture, but it's a conjecture. Let's see whether or not it's true. Okay, well, let's see. Blah, 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 blah. Well, let's start with linear algebra. Let's take the two-dimensional vector space R2, and let's take the standard complex structure and the standard metric. Well, let's calculate the star of E1. So what's the star of E1? Well, I know that E1 E1 wedge, the star of E1 should be E1, E2. Okay, now the star of E2 is, well, again, I use the fact that E2 wedge the star of E2 should be E1, E2. So here I get minus E1. Are there any questions or remarks?
I still don't understand. Are these two the same?
Which two are the same?
So in the E plus E is it minus?
Well, that's what we're trying to find out. We want to prove or disprove that these two decompositions are the same.
Okay, so we're not finished yet, right?
Not yet, but we've started. We haven't finished, but we've started. So we took the standard basis E1, E2 and calculated the star.
Okay, calculation of star, I understand.
Okay, now let's see. So okay, now let's calculate alpha. Alpha is I to some power times star. Now, what is the power? Well, it says what it is in question 14. Well, let's write it down. I need to take I to the power b minus 1 plus 1/2 n. Well, which is great, but what is n and what is b? Well, let's see. Well, n is the dimension of by the way, blah blah blah. Well, n is 2 in our case, and p is 1. Why? Well, because we consider the first exterior power of v. Okay, so we get I star. Does everyone agree with this? So in particular, we see that alpha has a matrix I 0 minus I 0. Okay, now let's let's do a sanity check. Alpha squared should be minus the identity. Okay, let's square this matrix. It shouldn't be too hard. Oh no, sorry, a plus identity. Well, so it says yes. So it says in question 14c. Okay, so by the look of this matrix, it does square to plus identity. Does everyone agree?
Yes.
Okay, so we have two vectors, eigenvectors, 1 minus I, and this one has eigenvalue 1, and 1 plus I with eigenvalue minus 1. Well, let's see. Is it the other way around? I think it's the other way around. Okay. And this one, minus 1, this one. Okay, again, check my calculations. It's always a good idea to check the lecturer's calculations. Does everyone agree that these are the eigenvectors with these eigenvalues?
Yes.
Hold on. Okay. Okay. Well, it looks like this is it. Okay. So and so as a consequence, L star, which will correspond to E minus, and L will correspond to E plus. So the compositions are indeed the same, but hold on. There's no. This is the way it's supposed to be. I'm looking ahead. I'm looking at the formula from which we want to prove, and this is the formula. Okay, so Okay, so now, let's not get ahead of ourselves. Does everyone agree that we have that we indeed have this decomposition, where L upper star corresponds to E plus and L corresponds to E minus? If we just remember where this one comes from, we we basically take the eigenvectors of we would we would basically take in the definition of L and L star, we basically take the same we use the same vectors, but these vectors were the eigenvectors of multiplication by I. Well, here we have a slightly different operator, I times multiplication by I. But the eigenvectors are the same because the operators are almost the same. Almost meaning one is a scalar multiple of the other. Someone, does this make any sense?
Yes.
Vladimir.
Well, yes.
Leonid.
Yes.
Okay. Now we've done question 15C for line bundles. And now we use the same not for line bundles, for oriented bundles of rank 2, real oriented rank 2. How we use the splitting principle, and the splitting principle says that if something is true after splitting, it was true before splitting. But we need to prove the following thing. Let's at least write it down. Okay, so suppose we have E is sum E1 plus etc. plus EM. Where all bundles are real, oriented, ranked. Now, Now I want this identity. Now, what does this identity? Well, first of all, where does this identity live? Well, it lives in K. In the K ring of X, where X is the base of all the bundles. Okay, now where does the formula come from? Well, the formula comes from the fact comes from basically question 15b, which says that the scale which says that the exterior algebra of the sum is the tensor product of the exterior algebras, and the map alpha is just it's just the tensor product of the individual alphas. So in particular, if I have okay, let me write it down. I have lambda of E is tensor product of lambda EI. So here I have alpha, which acts on the algebra E, or lambda E, and here I have the tensor product of the alphas. Leonid, does this make any sense? At
Yes.
least on the level of statements. Now these statements need to be checked, but this is linear algebra. Let's sweep it under the carpet. Okay. Now basically, once we have this formula in the K ring, we have the formula for the Chern classes. Sorry, for the Chern character. Saman, do you agree?
Well, can you explain more?
I'm sorry, I didn't quite catch what you said.
I mean, I said it's not immediate for me. Why it's enough to compute the Chern character?
Well, because of the splitting principle. Suppose I have some oriented vector bundle. I pull it back so that the result splits as a sum of rank 2 oriented real vector bundles. Now, upstairs, after splitting, I can use this this formula plus the fact that I know the Chern character of L. I know the Chern character of L upper star. The Chern character of L is e to the x. The Chern character of L upper star is e to the minus x, and and basically after splitting, I get precisely the product of the e to minus xi minus e to the xi.
Yes, now it's clear. Yeah, thank you.
Okay, now well, Leonid says he needs to go too. Okay, but we're almost done. And by the way, Zoom says we need to go. Anyway, as I say, well, question 15 is well is well, I think we did question 15c, which is the main part the main part of the proof in the signature case, which is different from the Durand case. The rest of the proof is exactly the same. We take the answer for the Durand operator and substitute in it the churn of lambda even minus odd by the churn of lambda plus minus lambda minus. Which is something that we know already. It's it's the product of e to the minus xi minus e to the xi. And the rest of the proof is exactly the same. Namely, we first construct the element we want to pull back in the cohomology of the Cosmanian, and more precisely, we construct this element times the Euler class, and then we use the fact that in the Cosmanian the Euler class is a non-zero divisor, so we can cancel it in the formulas. Okay, well, I suggest we stop here. Are there any questions? Okay, now if there aren't any questions, then let's let's meet on Tuesday, and we'll talk about some more examples of some more applications of the index theorem, and in particular, we'll hopefully prove the Riemann-Roch theorem for complex analytic manifolds, which is which is a particular case of the index theorem for the Dolbeault operator. Okay, I think I saved the notes. Well, is there anything else we need to talk about? Okay, then let's call it a day, and we'll see each other on Tuesday.
Thank you.
You're welcome.
Спасибо. До свидания.
Всего доброго.